Welcome to the deep dive. Today we're plunging into something pretty invisible, but absolutely crucial. It's the world of radio waves that, well, basically runs our modern lives.
It really does. Everything from your Wi-Fi, your mobile phone connection, Bluetooth, it's all happening on these airwaves.
Exactly. But here's the thing, and this is what kind of grabs you, these airwaves, or the radio frequency spectrum. Technically speaking, they're not infinite. Not at all.
Far from it. It's a finite resource, incredibly valuable, and most of it is already licensed out.
Right, license. But here's the paradox, isn't it?
Mm.
A lot of this licensed spectrum, this sort of prime digital real estate, often just sits there, underutilized.
It's a huge inefficiency. Think of it like owning a massive skyscraper in a bustling downtown area, but keeping most of the floors completely empty most of the time.
While everyone outside is desperate for office space.
Precisely. And that scarcity, that bottleneck, is a real drag on innovation, especially with how connected everything is becoming.
Okay, so that sets the stage perfectly for our main topic. Cognitive radio, or CR. This is supposed to be the smart solution, right?
That's the idea. Cognitive radio came about to tackle this very problem. It lets secondary users think of them as, I don't know, opportunistic renters use licensed bands intelligently.
But only when the primary users, the owners, aren't actually using them at that moment.
Exactly. It's about smart sharing, getting the most out of what we have without stepping on the original owner's toes.
For that whole system to work, for CR to be, viable, there's one absolutely critical piece.
Spectrum sensing, yeah. The secondary users have to know accurately whether the primary user is transmitting or not.
It's the absolute foundation, isn't it, if the sensing is off?
Chaos. You either get interference, which is bad news for the primary user, potentially disrupting critical services.
Or you get missed opportunities, where the secondary user thinks the band is busy when it's actually free, defeating the purpose of CR.
Right. So this sensing has to be incredibly reliable.
And that's the core challenge we're diving into today. Because traditional spectrum sensing methods, they really struggle in the real world.
Oh, absolutely. We're talking low signal strength, where the signal you're looking for is barely above the noise.
And the noise itself isn't stable. It's unpredictable, what they call noise uncertainty.
Plus, you've got signal fading, where the signal strength just fluctuates wildly because of the environment. These aren't small issues.
Not at all. So the research paper we're digging into today tackles these exact problems. It looks at advanced techniques, specifically something called Generalized Energy Detectors, or GEDs.
And it really gets into the weeds on how these detectors perform under tough conditions, especially when you use multiple receivers. And it explores this really fascinating, slightly scary concept called the SNR wall.
The SNR wall. Sounds ominous. So what are we hoping to uncover here?
Well, we'll see how these fundamental noise issues can actually create hard limits, these walls, on communication reliability.
But also how clever engineering, like using diversity schemes, can help push back against those limits.
Exactly. And we might find some surprising things about what actually degrades performance the most in the real world. It challenges some common assumptions.
Okay, sounds like a fascinating journey. Let's start with the basics then. This silent battle for bandwidth. Right. This idea of spectrum being scarce, it can feel a bit abstract maybe. It's not like running out of fuel you can see.
True, but the impact is very real. Most of the usable radio frequencies are already licensed. Think mobile carriers, TV broadcasters, emergency services. They've paid for exclusive rights to use specific chunks of spectrum.
Like owning plots of land, but in the airwaves.
A good analogy. But then studies consistently show that much of this licensed land is, well, empty a lot of the time, underutilized.
Which seems incredibly wasteful.
It is. It's like having a massive highway with, say, 20 lanes, but only ever using 3 or 4, while the entrance ramps are totally gridlocked.
That's a powerful image, and that gridlock, that bottleneck, directly impacts us, right? It slows down innovation.
Absolutely. Think about the explosion in wireless demand. More devices, faster speeds, the Internet of Things, 5G. It all needs spectrum.
Yeah.
If chunks of it are locked away and unused, it holds everything back.
So it's an economic issue, a societal issue, not just a technical one. We need more capacity, and just building more lanes isn't always feasible or efficient.
Exactly. And that's where cognitive radio comes in as such an elegant approach. It's not about building new highways, it's about intelligently using the empty lanes on the existing ones.
Letting those secondary users slip in when the primary user isn't there.
Right. And this becomes absolutely fundamental for future tech. The paper highlights things like the Internet of Things, IoT, and 5G.
Okay, let's connect that. Why are IoT and 5G particularly dependent on this kind of smart spectrum use? What's different about them?
It really boils down to scale and flexibility. Take IoT. You're potentially talking billions, maybe trillions of devices.
Right.
Many of them, like sensors, might only need to transmit tiny bits of data very infrequently, once an hour, once a day.
Giving each one a dedicated frequency would be insanely wasteful.
Well, unsustainable. CR lets them just grab a free slot when they need it, share the space efficiently.
Makes sense. And 5G.
5G is all about supporting hugely diverse applications simultaneously. You've got massive data rates for phones, super low latency for things like remote surgery or self-driving cars, and connecting vast numbers of simple devices.
So it needs access to a lot of different types of spectrum,
Yeah.
flexibly.
Exactly. It needs to dynamically access spectrum across low, mid, and high bands, depending on the need. CR principles allow 5G networks to be much more adaptable and efficient in grabbing whatever spectrum is available and suitable at that moment. If a TV channel is off-air in a certain region at night,
Why let that spectrum sit idle when a 5G network could use it temporarily?
precisely, it's about dynamic, intelligent utilization.
Okay, it clearly makes a ton of sense from an efficiency perspective. But, as you said earlier, the whole thing hinges entirely on that one crucial step, spectrum sensing.
It's the gatekeeper. The secondary user has to know if the primary user is there or not.
And if that sensing is wrong, we touched on this, but let's reiterate the stakes.
The stakes are high. A false negative thinking the band is free when it's not causes harmful interference. Imagine jamming an emergency frequency or messing up air traffic control signals. Not good.
Definitely not good.
And a false positive thinking the band is occupied when it's actually free means a missed opportunity. The secondary user doesn't transmit, and we're back to that same problem of underutilized spectrum.
So the sensing needs to be incredibly accurate. Not too sensitive, not insensitive. Just right.
Exactly. The margin for error is razor thin. It's a really challenging detection problem.
Okay, so sensing is key. How do we actually do it? Let's start with the most common, maybe the simplest approach, energy detection, or ED.
Right. ED is popular mainly because it's relatively easy to implement. And crucially, you don't need to know anything specific about the primary user signal beforehand.
You don't need its fingerprint, so to speak.
Exactly. No need to know its modulation type, data rate, anything like that. It just measures the total energy in the frequency band over a certain time.
And compares it to a threshold.
Yep. If the energy is above a preset threshold, it assumes the primary user is present. Below the threshold, it assumes the band is free.
It's like listening in a quiet room. You don't care what the sound is, just if there's enough sound energy to say someone's likely there.
That's a great analogy. Simple presence or absence based purely on energy level.
But simple often comes with a catch, right? What's the downside of ED?
The big catch is its performance. It really struggles, sometimes fails completely under challenging real-world conditions.
Like the ones we mentioned earlier.
Exactly. Low signal-to-noise ratio, or SNR, where the signal is weak compared to the background noise. Noise uncertainty, where that noise level itself is fluctuating and unpredictable. And fading, where the signal strength dips or varies wildly.
So in those common messy scenarios, ED just isn't reliable enough.
Often, no. It becomes very prone to making errors, either missing weak signals or falsely detecting noise as a signal.
Which brings us to the next step in the evolution. The Generalized Energy Detector, or GED. This is where the mat gets a bit more flexible, right?
It does, and this is where the paper really starts to dig in. GED builds on ED but makes one key change. Instead of just squaring the received signal amplitude,
Which is effectively raising it to the power of 2.
right, the GED replaces that fixed power of 2 with an arbitrary positive exponent, which they call P. So it's sometimes called a P-norm detector.
So the standard ED is just a GED or a P2.
Precisely. And the big deal is this flexibility in P. Previous research, which this paper acknowledges, found that choosing a different P, maybe 1.5 or 2.5 or 3.3, could actually improve detection performance in certain situations compared to just using P2.
Huh. So just tweaking that exponent gives you a potential advantage. How does that work intuitively?
Bro.
Why would raising the signal to the power of, say, 3 instead of 2 help?
That's a really good question. It changes how the detector weighs different parts of the signal energy. Think about it. Squaring P2 gives emphasis proportional to the signal strength. A higher P, like P3, gives much more weight to the stronger parts of the signal and relatively less weight to the weaker parts.
Okay.
So imagine you have a primary signal that's very bursty, short, strong pulses. A higher P might help the detector lock onto those strong peaks more effectively and distinguish them from lower level, steadier noise.
Ah, I see. It emphasizes the peaks.
Or conversely, maybe a different p-value, perhaps less than 2, might be better for detecting very weak but persistent signals buried in certain types of noise. It gives engineers a tuning knob, essentially.
A way to tailor the detector's sensitivity profile to the specific signal or noise characteristics they expect.
Exactly. That adaptability is what makes GED potentially more powerful than the simple fixed DD, especially when conditions get tough.
All right, let's talk about one of those tough conditions in more detail. Noise uncertainty and U. It sounds like a really fundamental problem.
It is. In theory, we assume we know the background noise level perfectly, but in reality, that noise floor is constantly shifting.
Why? What causes it to be so uncertain?
It's a combination of things, really. The paper points out a few key sources. You've got tiny calibration errors in the receiver hardware itself. Nothing's perfect.
Yep.
Then there's natural thermal noise, the random jiggling of electrons in the components, which changes with temperature.
Right, basic physics.
Then a big one, variations in the gain of the low noise amplifier, the LNA. That's the first stage amplifying the really weak incoming signal if its amplification fluctuates even slightly.
It changes the perceived noise level significantly.
Exactly. And on top of all that, you have environmental noise interference from other devices, other transmissions, atmospheric noise, which is inherently dynamic.
So it's not just a steady hiss, it's a complex, fluctuating background you're trying to detect a signal against.
Precisely. And that makes setting that decision threshold for the energy detector incredibly difficult. If the noise floor itself is moving up and down, where you set the bar to reliably catch a real signal without constantly getting false alarms from noise spikes.
It sounds like trying to measure ripples on the surface of a choppy sea.
That's a good way to put it. Even if you sense for a really long time, collect tons of data samples, this uncertainty limits your ability to make a confident decision.
And this difficulty, this fundamental limit imposed by NU, leads directly to this concept of the SNR wall.
Yes. The SNR wall is a direct consequence of noise uncertainty. It represents a specific signal-to-noise ratio value. Below this value,
Things break down.
completely. Below the SNR wall, you simply cannot achieve your desired detection performance, say perfect detection with 0 false alarms no matter how long you sense for. Even with infinite sensing time, infinite samples.
Wow, so it's not just about collecting more data. There's a point where if the signal is too weak relative to the uncertainty and the noise, detection becomes fundamentally impossible.
That's exactly it. It's a hard limit imposed by the physics of the situation and the imperfection of our knowledge about the noise. Think of it as a fundamental sensitivity floor.
A true wall.
And here's the critical thing that shows just how impactful noise uncertainty is. If there were no noise uncertainty, if you knew the noise level perfectly, the SNR wall wouldn't exist.
Really?
Yes. Without NU, you could theoretically detect any signal, no matter how weak, as long as its SNR is above 0, just by sensing for long enough. The wall only appears because of the noise uncertainty.
That really highlights it. NU isn't just a nuisance, it creates a fundamental barrier to reliable detection in low SNR scenarios. Okay, so noise uncertainty is a major hurdle, creating this SNR wall. But wireless signals face other gremlins too, right? We mentioned fading and shadowing earlier. Can we quickly recap those?
Sure. Multipath fading is when the signal takes multiple paths to reach the receiver, bouncing off buildings, hills, whatever. These paths have different lengths, so the signals arrive slightly out of sync.
And they can interfere with each other.
Right. Sometimes they add up constructively, making the signal strong. Other times, they cancel each other out destructively, causing a deep fade, a sudden drop in signal strength.
And shadowing.
Shadowing is more about large obstacles. A big building, a dense forest, a hill physically blocking the signal path. It causes slower, larger-scale drops in signal strength over an area, like when your cell signal disappears as you drive behind a big structure.
And relying on just one antenna, one receiver, makes you vulnerable to both of these.
Extremely vulnerable. If that single antenna happens to be in a deep fade spot or behind a shadowing obstacle, your signal is gone, regardless of how good your detector is.
So you need some way to increase resilience. Teamwork, maybe.
Exactly. That's where diversity schemes come in. The basic idea is to use multiple receive paths, usually multiple antennas spaced apart, to get independent looks at the signal.
So if one antenna is in a bad spot,
Hopefully another one isn't. It's about not putting all your eggs in one basket. It provides redundancy and makes the overall reception much more robust against these channel impairments.
makes sense. So the paper looks at combining these diversity ideas with the Generalized Energy Detector. What were the two main schemes they investigated?
They looked at two primary approaches: P-law combining, or PLC diversity, and P-law selection, or PLS diversity.
Okay, PLC first. How does combining work?
With PLC, you take the decision statistic, the energy value calculated using the exponent P from each of your diversity branches, each antenna. Then you simply add them all together.
Summing up the energy readings from all antennas.
Essentially, yes. The final decision, signal present or absent, is based on this combined sum statistic. It's like pooling all the information together.
Like everyone on the team contributing their piece of evidence. And you make a decision based on the total weight of evidence.
That's a good analogy. It leverages information from all paths.
Okay, and the other one, PLS P-law selection. How is that different?
PLS is simpler in a way. Instead of adding everything up, you just look at the decision statistics from all the branches and pick the maximum one.
So you find the antenna that's getting the strongest signal reading at that moment and base your decision solely on that one.
That's right. You just select the best performer among the branches and ignore the others for that decision instant.
Interesting. That's like listening to several people talking in a noisy room and just focusing on the loudest, clearest voice.
Exactly. So both PLC and PLS use multiple antennas to improve performance, but they do it very differently. PLC aggregates, PLS selects the best. Understanding which one works better under which conditions is a key part of the paper's investigation.
Okay, let's get into those findings now. The paper really dissected the SNR wall, starting with that simpler AWGN channel model, but importantly, still including noise uncertainty. What did they find for a single receiver? No diversity.
Right, so just one antenna, AWGN noise, but with that pesky noise uncertainty, NU.
Yeah.
They derived a mathematical formula for the SNR wall, and the key finding was perhaps a bit surprising.
Which was?
The SNR wall, in this single receiver case, is completely independent of the p-value in the generalized energy detector.
Wow. So fiddling with P doesn't help you overcome the wall if you only have one antenna. Whether you use P2 or P3 or whatever, the fundamental limit set by NU stays the same.
Exactly. The formula they derived, 10L to L, 10 pounds, where L is the noise uncertainty in dB, shows the wall depends only on L, the level of uncertainty, not on P. If L is 0, no uncertainty, the wall is 0 SNR, meaning perfect detection is possible. But any uncertainty L0 creates a wall, and P can't tear it down.
Okay, that's clear. But what happens when you bring in diversity? Let's start with PLC, the combining scheme. Does that change things?
It does, but it depends. The analysis gets more complex, especially if the noise uncertainty, L, or the average SNR, is different at each antenna, which is realistic.
So what did they find in those cases?
Two main things. First, if you have a homogeneous setup, meaning all antennas experience the same noise uncertainty, L1, L2L, and the same average SNR, then the SNR wall is still the same as the no diversity case, and it's still independent of P.
So just combining identical inputs doesn't magically make EP matter for the wall itself.
Not for the wall location, no. The combining still helps fight fading, but doesn't change the fundamental pain independence of the NU-induced wall in this specific scenario.
But what about the more realistic heterogeneous case, where the SNRs are different at each antenna?
Now it gets interesting. This is a huge finding. When the SNRs differ across branches, the SNR wall does become dependent on the value of P.
Really? So P suddenly matters?
Yes. And crucially, they found that increasing the value of P when using PLC diversity with unequal SNRs can actually lower the SNR wall.
Lowering the wall means better performance, right? You can detect weaker signals reliably.
Exactly. A lower wall is always better. It means you need less signal strength to achieve that unlimited reliability.
Can you give an example? How much difference can P make here?
The paper gives a numerical example. 2 branches, both with L1 dB noise uncertainty. Let's say branch 2 has a low SNR, below 0.1. To achieve unlimited reliability, the required SNR on branch 1, which is the wall in this context, decreased as P increased. For P1, you needed GUL 1.8914, but for PP5, you only needed GUL 1.7153.
That's a reduction of almost 1 dB. That's significant in wireless terms.
It really is. It shows that with PLC, if you have at least one branch with a decent signal, even if others are weak, optimizing P helps you leverage that good branch more effectively to overcome the wall.
Okay, that's powerful for PLC. What about PLS, the selection diversity, where you just pick the best signal? How does the wall behave there?
For PLS, the finding was simpler. The SNR wall is independent of P, just like the no diversity case.
So no benefit from tuning P with selection diversity when it comes to the wall.
Correct. But PLS has a different kind of advantage. For unlimited reliability with PLS, you only need the SNR at any single branch to be above its own SNR wall.
Ah, it's an or-R condition, not an ADD. So if antenna 1 has SNR above its wall or antenna 2 has SNR above its wall, you're good.
Exactly. Using their example, if L1.5 dB wall, wall 0.23, and L2.319, you just need either over 0.23 or away 0.23 or well 4.19.
That sounds incredibly resilient.
That's it.
One good antenna path can basically save the day, even if the others are terrible.
That's the key benefit of PLS. It's robust because it only relies on the best instantaneous condition available across all branches.
Okay, that covers the AWGN case.
Hmm.
Now let's make it even more real by adding fading. They use the Nakagami fading model, right?
Yes, Nakagami fading, which is quite general and can represent various environments from mild to severe fading.
So you've got noise uncertainty, A and D fading now. What does that do to the SNR wall?
It makes it significantly worse. The paper shows that when you consider both NU and fading, the SNR wall increases substantially compared to the NU-only case.
Meaning you need a much stronger signal to achieve reliable detection.
Much stronger. Fading adds another layer of difficulty on top of the uncertainty. And interestingly, they noted that for fading channels, they couldn't find a neat mathematical formula for the wall. They had to rely on numerical simulations to find its value.
Can you give us a number to illustrate how much worse it gets?
Sure. For P2, L is 0.5 dB noise uncertainty and a moderate Nakagami fading parameter M2. The SNR wall without diversity jumped from 0.2308 AWGN with NU to 1.841 fading with NU.
Whoa, that's a huge jump, almost 8 times higher in linear terms, or over 8 dB.
It's a very significant increase, yes, around 9 dB actually. It highlights how much harder fading makes the detection problem, especially when coupled with noise uncertainty.
But diversity still helps, even in these really tough fading conditions.
Oh, definitely. It's even more crucial here. For example, using PLC diversity with P2, LGIL 0.5 dB, M plus 2 on both branches, the SNR wall came down to 0.67 for each branch.
Okay, 0.67 is still higher than the EWGN case, but much, much better than the 1.841 without diversity and fading.
Exactly. It shows diversity provides substantial gains, pushing that wall down considerably, even when facing both NU and fading. And for PLS and fading, the wall remained independent of P just like before.
This is incredibly insightful about the fundamental limits. But the paper went beyond just the wall, right? It looked at overall performance and offered practical takeaways. What about the optimal p-value for the GED in general use?
Yes, they looked at detection probability, not just the wall. And this is a key practical finding for sufficiently high sample sizes, N, meaning you have a decent amount of sensing time or data.
Which you'd want in a real system.
Right. In that case, the GED performs best when P is close to 2.
So, back to the standard energy detector.
Pretty much. It suggests that while other p-values might offer theoretical advantages in specific niche cases or with very few samples, as some older research suggested, once you have enough data, the robustness of the P2 squaring operation often wins out for overall performance.
This simplifies things for designers, doesn't it? For many practical systems, sticking with P2 might be the best bet.
It certainly suggests that, yes. It implies that conventional ED is actually quite optimal when you can afford a reasonable number of samples.
Okay, what about comparing the two diversity schemes head-to-head? PLC combining versus PLS selection. Which one generally performed better overall?
The results showed that PLC diversity, the combining method, generally performs better than PLS diversity.
Better detection probability.
Yes. They gave an example. With P2 and N500 samples, PLC achieved about 30% higher detection probability than no diversity, and crucially, about 7.2% higher detection probability than PLS under the same conditions.
So adding up the information from all branches usually gives you a better result than just picking the best one.
Generally, yes. It seems that aggregating the energy provides a more robust final statistic.
But there was that interesting point about what happens with tons of data, right? The asymptotic case.
Yes, the aha moment
Yeah.
as the number of samples N goes towards infinity.
Which is theoretical, but tells us about fundamental limits.
Exactly. As N gets extremely large, two things happen. First, the detection performance of the GED becomes independent of P. The choice of exponent doesn't matter anymore.
So P2, P3, whatever, they all converge.
They converge in performance. And second, the performance of both PLC and PLS diversity schemes becomes almost the same.
Wow. So with infinite data It doesn't matter if you combine or select, and it doesn't matter what P you use.
Essentially, yes. The sheer amount of information dominates any subtle differences in the processing method. It implies that for systems that can integrate over very long times, the specific detector design choices become less critical.
Fascinating. Now, maybe the biggest takeaway described as a byproduct of their work, comparing noise uncertainty versus fading, which is the bigger villain.
This is a really significant finding. They directly compared the impact of NU versus the impact of fading on the GED's performance, and the result might challenge some long-held assumptions.
How so?
For certain levels of noise uncertainty, its negative effect on detection performance is actually more severe than the effect of fading alone.
Really? Worse than fading. Fading gets so much attention in wireless design.
It does, but their ROC curve analysis showed it clearly. For instance, with L.4 dB uncertainty, the detection probability was significantly lower, around 21% lower at a P of 0.1, compared to having only fading present with M2.
That is a huge difference. It suggests maybe we haven't paid enough attention to accurately characterizing and mitigating noise uncertainty.
That's a strong implication. While fading is undeniably a problem, this research suggests that NU can be the dominant limiting factor in some realistic scenarios. Ignoring it, or assuming it's negligible, could lead to designs that significantly underperform in the real world.
And of course, performance is worse when you have both NU and fading together.
Predictably, yes. That's the toughest but also the most realistic scenario.
So the big implication here is,
Engineers really need to focus on understanding and mitigating noise uncertainty. It's not a secondary effect. It can be a primary bottleneck, sometimes even more damaging than fading. Techniques for better noise estimation, calibration, and designing detectors robust to NU are critical for reliable cognitive radio and maybe wireless systems in general. Hashtag tag outro.
wow. Okay, we've covered a lot of ground in this deep dive, from the fundamental problem of spectrum scarcity,
To the elegant idea of cognitive radio trying to solve it.
then into the nitty-gritty of spectrum sensing, starting with basic energy detection.
And evolving to the more flexible generalized energy detector and that interesting role of the P parameter.
And then confronting that really challenging concept, the SNR wall, driven primarily by noise uncertainty.
A fundamental limit, yeah. But we also saw how clever techniques like diversity, especially PLC combining, can help us fight back against that wall, even when facing both noise uncertainty and difficult feeding conditions.
So summing up the key takeaways, the real headline messages from this research.
I'd say first, that surprising severity of noise uncertainty. It can be more detrimental than fading sometimes, which really shifts the focus for designers.
Right. Second, the nuanced story of the p-value in GEDs. Optimal near 2 with enough data, but ultimately becoming less important with massive data sets or when facing the SNR wall alone.
And third, the general performance advantage of combining diversity, PLC, over selection, PLS, although both offer huge benefits over no diversity. And asymptotically, they perform similarly.
It really paints a picture of the complex interplay between signals, noise, uncertainty, and the clever engineering needed to make wireless communication reliable.
It absolutely does. It shows that pushing the boundaries of wireless communication isn't just about brute force. It's about deeply understanding these fundamental limits and finding smart ways to work around them.
So let's leave everyone with a final thought to chew on. Given these findings, especially about noise uncertainty being such a major culprit, what if engineers really crack the code on characterizing and mitigating NU much more effectively than we do now?
That's an interesting question.
Could that breakthrough unlock vast amounts of spectrum that we currently consider unusable because the signals are just too close to that uncertain noise floor? Could tackling NU be a key enabler for, say, 6G or for making IoT truly ubiquitous and ultra-reliable?
It's definitely plausible. If you can effectively lower or manage that noise uncertainty L value we talked about, you directly lower the SNR wall. That could potentially open up operation in regimes that are currently off limits.
Making our use of the spectrum even more efficient, just by getting better at understanding the static.
It's a compelling thought. Maybe the next big leap isn't just about fancier signals, but about truly mastering the noise.
What stood out to you listening to this? Did you have any aha moments about this invisible world? We'd love to hear them. Thanks for joining us on the Deep Dive.